Dark matter. Dark matter is an invisible form of matter that makes up approximately 27% of the universe's total mass and energy. Unlike ordinary matter that we can see and touch, dark matter does not emit, absorb, or reflect light, making it completely transparent to electromagnetic radiation. Scientists know it exists because of its gravitational effects on visible matter throughout the cosmos. The evidence for dark matter comes from multiple astronomical observations. When astronomers measure how fast stars orbit around the centers of galaxies, they find these stars are moving much faster than they should be based on the visible matter alone. According to Newton's laws of gravity, stars at the outer edges of galaxies should orbit slowly because there appears to be less mass to hold them in orbit. Instead, these outer stars maintain high orbital speeds, indicating there must be additional invisible mass providing extra gravitational pull. Galaxy clusters provide another crucial piece of evidence. These massive collections of galaxies are held together by gravity, but the visible matter in the clusters is not nearly massive enough to generate the gravitational force needed to keep the galaxies from flying apart. The presence of dark matter, roughly 5 times more abundant than ordinary matter, provides the additional gravitational binding force required to maintain these structures. Gravitational lensing offers direct observational proof of dark matter's existence. When light from distant galaxies passes near massive objects, the gravity of those objects bends the light's path, creating distorted or multiple images of the background galaxies. Astronomers observe this lensing effect in regions where there is insufficient visible matter to cause such strong gravitational bending, confirming the presence of invisible dark matter. Dark matter has specific properties that distinguish it from ordinary matter. It is described as cold, meaning dark matter particles move slowly compared to the speed of light. It is also collisionless, meaning dark matter particles rarely interact with each other or with ordinary matter. These properties allow dark matter to pass through ordinary matter without any noticeable effect, which is why dark matter particles are constantly streaming through Earth and our bodies without detection. Scientists have proposed several candidates for what dark matter particles might be. Weakly interacting massive particles, known as WIMPs, are theoretical particles that would have significant mass, but interact only through gravity and the weak nuclear force. Actions are hypothetical particles that would be extremely light and interact very weakly with ordinary matter. Sterile neutrinos are proposed heavy cousins of known neutrinos that would not participate in normal nuclear reactions. Despite decades of searching, scientists have not directly detected dark matter particles. Underground laboratories around the world use ultra-sensitive detectors cooled to near absolute zero, waiting for the rare collision between a dark matter particle and detector material. Space-based telescopes search for high-energy gamma rays that might be produced when dark matter particles annihilate each other. Particle accelerators attempt to create dark matter particles in high-energy collisions, but none of these methods have yet succeeded in confirming the nature of dark matter. Dark matter played a crucial role in the formation of cosmic structure. In the early universe, dark matter began clumping together under its own gravity before ordinary matter could do the same. These dark matter clumps, called halos, provided the gravitational scaffolding around which ordinary matter could collect to form the first stars and galaxies. Without dark matter, the universe would look completely different, with far fewer galaxies and much less complex structure. Dark energy. Dark energy is a mysterious force that makes up approximately 70% of the universe's total mass and energy content. Unlike matter, which pulls things together through gravity, dark energy acts like an anti-gravity force that pushes space itself apart, causing the expansion of the universe to accelerate over time. The discovery of dark energy came from observations of distant supernovae in the 1990s. 2 teams of astronomers were studying type Ia supernovae, which are stellar explosions that always produce the same amount of light, making them useful as cosmic distance markers. These scientists expected to find that the universe's expansion was slowing down due to the gravitational pull of all the matter it contains. Instead, they discovered that distant supernovae appeared dimmer than expected, indicating they were farther away than predicted. This meant the universe's expansion was actually speeding up rather than slowing down. Dark energy has bizarre properties that distinguish it from all other known forms of matter and energy. As the universe expands and ordinary matter becomes more spread out and diluted, dark energy maintains a constant density throughout space. This means that as the universe grows larger, the total amount of dark energy increases proportionally, providing an ever stronger push that accelerates cosmic expansion. The leading explanation for dark energy is Einstein's cosmological constant, a mathematical term he originally added to his equations of general relativity to allow for a static universe. Einstein later called this his greatest blunder, when Edwin Hubble discovered that the universe was expanding. However, the cosmological constant represents the energy density of empty space itself, which could explain dark energy's constant density and repulsive effect. Quantum mechanics suggests that empty space is not truly empty, but filled with virtual particles that constantly pop into existence and disappear. These quantum fluctuations should contribute energy to the vacuum of space, potentially explaining dark energy. However, when physicists calculate how much energy these quantum effects should produce, their answer is larger than the observed amount of dark energy by a factor of 10 to the power of 120, making this the worst prediction in the history of physics. Alternative theories propose that dark energy might be a dynamic field that changes over time, similar to the field that drove cosmic inflation in the earliest moments after the Big Bang. Some models suggest dark energy could decay or transform into other forms of matter and energy, while others propose it might interact with dark matter in ways we do not yet understand. Dark energy's dominance began approximately 5 billion years ago, when the universe had expanded enough that matter became sufficiently diluted. Before this transition, matter and radiation controlled cosmic expansion, causing it to decelerate. Once dark energy took over, the expansion began accelerating and will continue to do so indefinitely, eventually carrying all galaxies beyond our observable horizon and leaving our local group of galaxies isolated in an increasingly empty universe. The ultimate fate of the universe depends on dark energy's behavior. If dark energy remains constant, the universe will continue expanding and cooling forever, with stars eventually burning out and leaving behind a cold, dark cosmos. If dark energy grows stronger over time, it could lead to a Big Rip scenario where the accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms themselves. Ordinary matter. Ordinary matter, also called baryonic matter, makes up everything we can see and touch in the universe. This includes all atoms composed of protons, neutrons, and electrons that form stars, planets, gas clouds, and living organisms. Ordinary matter accounts for approximately 5% of the total mass and energy in the universe, making it surprisingly rare compared to other forms of matter. Protons and neutrons, which make up atomic nuclei, are themselves composed of smaller particles called quarks. Protons contain 2 up quarks and 1 down quark, while neutrons contain 1 up quark and 2 down quarks. These quarks are held together by the strong nuclear force, mediated by particles called gluons. Electrons orbit the nucleus and belong to a different class of particles called leptons, which do not experience the strong nuclear force. The 4 fundamental states of ordinary matter are solid, liquid, gas, and plasma. In solids, atoms are tightly packed and vibrate in fixed positions around equilibrium points. The strong intermolecular forces keep the atoms locked in rigid structures, giving solids their definite shape and volume. Examples include ice, metals, and crystalline structures where atoms arrange themselves in repeating patterns. In liquids, atoms have enough thermal energy to overcome some intermolecular forces, allowing them to move past each other while remaining close together. Liquids maintain a definite volume, but take the shape of their container because the atoms can flow and rearrange themselves. The intermolecular forces are still strong enough to keep the atoms from separating completely, which is why liquids are nearly incompressible. In gases, atoms or molecules have sufficient thermal energy to overcome most intermolecular forces and move freely through space with large distances between particles. Gases have neither definite shape nor definite volume, expanding to fill any container completely. The particles move in random directions and collide elastically with each other and container walls, creating pressure through these molecular impacts. Plasma forms when gas becomes so hot that electrons gain enough energy to escape from their atomic nuclei, creating a soup of free electrons and positively charged ions. This 4th state of matter requires extremely high temperatures, typically thousands of degrees, which is why plasma naturally occurs in stars, lightning bolts, and the solar wind. Despite being rare on Earth, plasma makes up over 99% of all visible matter in the universe. Ordinary matter follows the laws of chemistry and physics that govern atomic interactions. Atoms combine through chemical bonds to form molecules and compounds, with the electron configurations determining how different elements interact with each other. The periodic table organizes all known elements based on their atomic structure, with each element defined by the number of protons in its nucleus. Nuclear reactions can transform one element into another by changing the number of protons in atomic nuclei. Nuclear fusion combines lighter nuclei to form heavier ones, releasing enormous amounts of energy in the process and powering stars throughout the universe. Nuclear fission splits heavy nuclei into lighter fragments, also releasing energy and forming the basis for nuclear power and weapons. Antimatter. Antimatter consists of particles that have the same mass as ordinary matter particles, but carry opposite electric charges and other quantum properties. For every type of particle in ordinary matter, there exists a corresponding antiparticle with reverse characteristics. When a particle and its antiparticle meet, they annihilate each other completely, converting their entire mass into pure energy, according to Einstein's equation E equals mc squared. The antiparticle of an electron is called a positron, which carries a positive electric charge instead of the electron's negative charge. Antiprotons have negative electric charge compared to the positive charge of ordinary protons, while antineutrons have reversed magnetic properties, despite both neutrons and antineutrons being electrically neutral. These antiparticles can combine to form antiatoms, with positrons orbiting around antinuclei made of antiprotons and antineutrons. Scientists first discovered antimatter in 1932, when physicist Carl Anderson observed positron tracks in a cloud chamber while studying cosmic rays. The positrons appeared as curved particle tracks that bent in the opposite direction from electrons when passing through magnetic fields. This discovery confirmed theoretical predictions made by physicist Paul Dirac, who had mathematically predicted the existence of antiparticles several years earlier. Antimatter production occurs naturally in several cosmic processes. High-energy cosmic rays striking Earth's atmosphere create particle showers that include both matter and antimatter particles. Certain types of radioactive decay, called beta-plus decay, produce positrons when protons in unstable nuclei convert into neutrons. Some astronomical objects, including pulsars and black hole accretion disks, generate antimatter through extreme magnetic fields and high-energy particle interactions. Laboratories can artificially create antimatter using particle accelerators that smash high-energy particles together. These collisions produce particle-antiparticle pairs from the kinetic energy of the impact. The European Organization for Nuclear Research, known as CERN, operates facilities that can produce and briefly store small quantities of antihydrogen atoms, which consist of antiprotons orbited by positrons. Storing antimatter presents enormous technical challenges, because any contact with ordinary matter results in immediate annihilation. Scientists use magnetic and electric fields to trap charged antimatter particles in vacuum chambers, preventing them from touching the container walls. Even with these sophisticated containment systems, antimatter can only be stored for minutes or hours before it eventually encounters stray matter particles and annihilates. The universe contains vastly more ordinary matter than antimatter, creating what physicists call the matter-antimatter asymmetry problem. According to current understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter, which would have completely annihilated each other, leaving behind only energy. The fact that matter dominates suggests there were subtle differences in how matter and antimatter behaved in the early universe, allowing a small excess of matter to survive. Antimatter represents the most energy-dense fuel theoretically possible, as complete matter-antimatter annihilation converts 100% of mass into energy. This makes antimatter attractive for theoretical spacecraft propulsion systems, as even tiny amounts could provide enormous thrust. However, the extreme difficulty and cost of producing and storing antimatter makes such applications purely speculative with current technology. Exotic states of matter. Exotic states of matter exist under extreme conditions that are rarely found in everyday experience, requiring temperatures near absolute zero or extraordinarily high energies to form. These states exhibit quantum mechanical properties on macroscopic scales, creating behaviors that seem to defy common sense and classical physics. Bose-Einstein condensates form when gases of certain atoms are cooled to temperatures within billionths of a degree above absolute zero. At these extreme temperatures, thousands or millions of atoms lose their individual identities and merge into a single quantum mechanical entity that behaves like one giant atom. The atoms occupy the same quantum state and move in perfect synchronization, creating a new phase of matter that acts more like a wave than a collection of particles. Scientists first created Bose-Einstein condensates in laboratory conditions in 1995, using rubidium atoms trapped by magnetic fields and cooled with laser techniques. The condensate appears as a dense cloud of atoms that can flow without friction, similar to a superfluid, and can be manipulated using magnetic and optical fields. These condensates allow researchers to study quantum mechanics on scales large enough to observe directly. Fermionic condensates represent another ultra-cold quantum state, but they form from atoms that follow different quantum statistics than those in Bose-Einstein condensates. Fermions, which include particles like electrons and certain types of atoms, normally cannot occupy the same quantum state due to the Pauli exclusion principle. However, at extremely low temperatures, pairs of fermions can bind together and behave collectively like bosons, allowing them to form condensates similar to Bose-Einstein condensates. Superfluids are liquids that flow without any viscosity or friction, allowing them to climb up container walls and flow through impossibly narrow spaces. Liquid helium becomes superfluid when cooled below 2.17 Kelvin, creating a state where the liquid can flow in circles forever without slowing down. Superfluids can also exhibit fountain effects, where the liquid spontaneously flows upward through narrow tubes due to quantum mechanical pressure differences. Superconductors are materials that conduct electricity with zero electrical resistance when cooled below a critical temperature. In the superconducting state, electrons form pairs called Cooper pairs that can move through the material without scattering off atoms or impurities. This allows electric currents to flow indefinitely without energy loss and enables superconductors to expel magnetic fields completely, causing magnets to levitate above superconducting surfaces. Time crystals represent a recently discovered exotic state, where the structure of matter repeats in time rather than space, similar to how ordinary crystals have repeating spatial patterns. These systems oscillate between different configurations in a regular cycle without any external energy input, appearing to violate conservation of energy while actually maintaining it through quantum mechanical effects. Time crystals exist in a state of perpetual motion at their lowest possible energy level. Quantum spin liquids are magnetic materials where atomic spins remain in constant fluctuation even at absolute zero temperature, never settling into a fixed magnetic pattern. Unlike ordinary magnets, where spins align in regular arrangements, quantum spin liquids maintain quantum entanglement between spins across large distances, creating exotic properties that could potentially be useful for quantum computing applications. Degenerate matter. Degenerate matter forms when ordinary matter becomes compressed to such extreme densities that quantum mechanical effects dominate over thermal motion. In this state, particles are packed so tightly together that they cannot be compressed further without violating fundamental quantum principles, creating matter with properties unlike anything found on Earth. Electron degeneracy occurs when electrons in a material are squeezed into the lowest available energy states, filling up all possible quantum levels up to a maximum energy called the Fermi energy. The Pauli exclusion principle prevents multiple electrons from occupying the same quantum state, so additional compression requires forcing electrons into higher energy levels. This creates a degeneracy pressure that resists further compression, independent of temperature. White dwarf stars consist primarily of electron-degenerate matter, formed when stars similar to our Sun exhaust their nuclear fuel and collapse under gravity. The star's core contracts until electron degeneracy pressure balances gravitational compression, creating an object roughly the size of Earth, but containing the mass of the Sun. White dwarfs have densities of approximately 1 million grams per cubic centimeter, meaning a teaspoon of white dwarf material would weigh as much as a car. The maximum mass for a white dwarf star is approximately 1.4 solar masses, known as the Chandrasekhar limit. Beyond this mass, electron degeneracy pressure cannot support the star against gravitational collapse, and the star will either explode as a Type Ia supernova or collapse further into a neutron star. This mass limit depends on the composition of the white dwarf, with heavier elements allowing slightly higher maximum masses. Neutron degeneracy creates even denser matter when gravitational forces become strong enough to overcome electron degeneracy pressure. Under these extreme conditions, electrons and protons are forced together to form neutrons through inverse beta decay, creating matter composed almost entirely of neutrons packed at nuclear density. Neutron degeneracy pressure, arising from the Pauli exclusion principle applied to neutrons, provides the support against further gravitational collapse. Neutron stars represent the most extreme form of degenerate matter that can be directly observed. These objects typically contain 1.4 to 2 solar masses, compressed into a sphere only 20 to 25 kilometers in diameter. The density of neutron star matter reaches approximately 500 million tons per cubic centimeter, meaning a sugar cube-sized piece would weigh as much as Mount Everest. The interior structure of neutron stars varies with depth, creating different phases of degenerate matter. The outer crust consists of heavy atomic nuclei embedded in a sea of degenerate electrons, while the inner crust contains neutron-rich nuclei and free neutrons. The core may contain exotic particles like hyperons, kaons, or even quark matter, though the exact composition remains uncertain due to the extreme conditions involved. Quark degeneracy might occur at densities even higher than those found in neutron stars, where the strong force can no longer confine quarks within individual neutrons and protons. In this state, quarks would exist freely in a degenerate quark soup, potentially forming strange quark matter or other exotic quark phases. Some theoretical models suggest that the cores of the most massive neutron stars might already contain degenerate quark matter. Dark matter is scary, but do you know what else is scary? Watch this video about the truth of black holes.